Okay. So, next you will please come to that voltage stability index, right. So, from this is equation 80. So, a feasible solution is possible if b square j j minus 4 c j j greater than equal to 0, because this is b square j j minus 4 c j j, it is to the power half. Therefore, this b square j j minus 4 c j j greater than equal to 0, right. So, that means it has to be this condition. So, and b j j and c j j all have been defined before, right. Therefore, from equation 77, 78 and 81 we get, that means equation 77 and 78 is b j j and c j j, that means here it is. This is your 77 is b j j and this is your c j j, these two equations, right. So, if you put those things b and c j j, b j j and c j j value here, then it will be your V m square magnitude, of course, minus 2 p m 2 r j j minus 2 q m 2 x j j, right, this whole square minus your 4 into r square j j plus x square j j into p square m 2 plus q square m 2 greater than equal to 0. This is equation 80. Now, you simplify this equation. I am writing only the final form after simplification. This you can easily do it. This square term you expand, these two terms you multiplication you just multiply and simplify, right. You will get V m to 1 to the power 4 minus 4 into p m 2 x j j minus q m 2 r j j whole square minus 4 into p m 2 r j j plus q m 2 x j j multiplied by magnitude V m square greater than equal to 0. This is equation 83, right. Then you assume, let us assume S I m 2 is equal to this whole term. So, it is V m 1 to the power 4, actually this is V m 1 to the power 4 minus 4 into this term, right, this term minus 4 into this term. That this is greater than equal to 0 means S I m 2 value also will be greater than equal to 0, and this S I m 2 we are defining as a stability index. So, this is equation 84. Now, this S I m 2 actually voltage stability index of node m 2, right. So, this because this is we are taking that your what you call that from that quadratic equation only. So, this is actually stability index for node m 2, this whole thing we are defining as a stability index, voltage stability index, right. So, that is for of node m 2, that is m 2 is equal to 2 3 up to node n b, right. N b is the total number of nodes of the network. For stable operation of the radial distribution networks, S I m 2 must be greater than equal to 0 for m 2 is equal to 2 3 up to n b. So, by using this voltage stability index, one can measure the level of stability of radial distribution networks, and thereby appropriate action may be taken if the index indicates a pole level of stability. I mean it has to be greater than equal to 0, but by chance if you find it is very close to 0 or maybe much less than 0.4, 0.3, 0.5 something like that, then you have to take some appropriate measure such that it will remain voltage stable, right. So, after the load flow study, suppose you are running the load flow, then all the all the voltages of all the nodes are known, voltage magnitudes are known, branch currents also are also known after the load flow studies, right. So, and P m 2, P m 1 and your P m 2 and Q m 2, this is P m 2, sorry, this is actually P m 2. P m 2 and Q m 2, right, for m is equal to 2 3 n b can easily be computed using equation 56 and 57 or equation 58 and 59. This all this expression is given for the second load flow case. For equation 56 and 57, at that time branch losses are there, right, but in 58 or 59 when is the last node there was no branch losses, right. So, only one term I explained also, although sigma symbol is there in that, but is equal to it is only one term, that also I have explained, right. So, all this can be computed using that load flow technique. That means, that load flow is required, because after load flow only you will get all these things, right. Similarly, for the fast load flow also it is possible right, to get P m 2 and Q m 2, but we will stick to it that only, right. Hence, one can easily calculate the voltage stability index of each node, that is M2 is equal, after load flow studies all the results are known, voltage magnitude and PM2 and QM2 all are known for M2 is equal to 2, 3 up to NB, NB is the total number of nodes. Therefore, you can calculate SI2, SI3 and so on up to SINB, right. Therefore, node at which the value of the sensitivity index is minimum, that node is more sensitive to the voltage collapse. For example, here it is SIM2 is this one, M2 SI2, SI3 all you will calculate up to SINB, and your condition is that SIM2 will be greater than equal to 0, right. But node at which this voltage value will be minimum, that node actually is more sensitive to the voltage collapse, right. And therefore, SI mean, that is your is equal to minimum of SI2, SI3 and SINB, right. For example, SI mean is equal to say SIK, the kth SI value, right, where it is minimum, where node K is the most sensitive to voltage collapse, and this is because this one is giving the same minimum value. Say this is equation 86, this is equation 87. You have to compute for SI values for all the nodes. After that, you take the minimum of that and corresponding to that node. That is why this S minimum is equal to SIK, K is that kth node, and this SIK value is the minimum one, right. And for example, in a distribution system, you have just for the purpose of this thing, for a distribution system, suppose total load is this one and TQL. Suppose you have that your PL, say PLI is equal to say nominal load, that means initially load was PLI, right, multiplied by some factor alpha. Similarly, say QLI is equal to say initial load QLI into alpha. So, that means total, when you find out this TPL actually is given in megawatt, TPL is equal to alpha times PL0 I is equal to 2 to NB, and TQL is equal to alpha times I is equal to 2 to NB, it is QL0 I, right. So, this total, this is the this side is TPL is the total load. Now, for assuming that all the loads of all the nodes are increased uniformly, for example, alpha is equal to say 1.05, 1.10, this way you go on increasing, right. So, in that case, every time you find out, every time you increase this, take this value for all the loads, you load is increasing, you increase uniformly to all the loads, assuming that load growth is there, just to test it, right. And once you are doing it, then you will find this SI mean value gradually will decrease. This is the maximum value 1, right, and gradually it will decrease, and here also SI mean gradually they are decreasing, the maximum value is say 1, right. Therefore, this is TQL. If you plot somewhere, you will come somewhere, you will find after that there will be no solution for your that voltage magnitude. So, just before that your what you call the system voltage will collapse. For example, here substation voltage is always 1, right. Suppose if you take for the M2 is equal to 2 and M1 is equal to 1 for branch 1, this voltage is always 1. Suppose these are not there, PM2, XJJ, RJJ is there. Suppose PM2, KM2, PM your at node 2, suppose there was the total load in the distribution network, so nothing is there. Suppose all load is 0. So, if you use this expression, you will find SI value will be 1, right. That is why this value is starting from 1, right. That is why it is starting from 1, assuming that substation voltage is 1, right. If it is 1.025, say it will go up somewhere here, right. It will be more than that, because it is Vm1 to the power 4. So, in any way, so but that is why it is starting from 1. So, if you go on, it is almost not linear exactly, curvilinear, but gradually you will find at some point there will be no solution and system voltage will collapse, right. So, I will take an example, suppose just to show you that we will use that second your what you call after second iteration, whatever we have done, that method 2 data, load flow data. So, after second iteration we got P2 is equal to 0.01536918 per unit. Q, this all data taking after the load flow studies from method to second iteration, right. Everything has been explained, all these are given, just have a look, but for rather than going to those pages, everything I have rewritten, right. Similarly, Q2 is equal to 0.01111512 per unit, P3 is equal to 0.01110391 per unit, and Q3 is equal to 0.00804317 per unit. Similarly, P4 0.006, Q4 0.004. These data are available. After second iteration, these are the voltage magnitude. V2 was 0.985739 per unit, V3 was 0.96579 per unit, and V4 0.951207 per unit, and all R value and X value in per unit, they are all per unit, they are same, all R1 X1, R2 X2, R3 X3. Here everything I am putting in bracket, so I should put it here in bracket, right. So, all these things R1 X1, R2 X2, R3 X3 all are in per unit. This data we have used earlier, but in per unit value rewritten here. So, using this data we will calculate SI2, SI3 and SI4, because it is a 4 node problem. So, using equation 84, this is my expression for SIM2, this is expression. So, when Jj is equal to 1, M1 is equal to 1, M2 is equal to 2. So, what you just to give you a flavor of the voltage stability index. Therefore, SI2 is equal to V1 to the power 4 minus whatever is given here, you put P2 x1 minus Q2 R1 whole square minus 4 into P2 R1 plus Q2 x1 into magnitude V1 square, right. So, put all these value, because all these data are given, all these data are given after second method 2, after second iteration method. So, if you put all these values, you will get, it will come, actually it is 1. So, 1 minus 8.67 into 10 to the minus 6 actually minus 0.0561. So, it is approximately 0.94378, that is the voltage stability index value at node 2. Similarly, find out node 3 and node 4. Similarly, when Jj is equal to 2, M1 is equal to 2, M2 is equal to 3, right. Therefore, Si3 is equal to V2 to square minus 4 into this term minus 4 into this term into V2 square. All this voltage V1, V2, everything is given, all these values are available, voltage V3 here it is, everything is available, right, after second iteration. So, put all these values, if you do so and substitute and compute, it is actually now V2 square. So, 0.985739 minus this one whole square minus this one into your V2 square. So, it is 0.985739 square. So, you simplify, it is Si3 is equal to 0.94416 minus 8.88 into 10 to the power minus 5 minus 0.07483, this is coming 0.86924, right. Similarly, for Jj is equal to 3, M1 is equal to 3, M2 is equal to 4, put this thing and get this expression, right. In the expression, that is same expression of SIM2, you put this thing, get this expression and put all these value, this is 0.596579, that V3 values, right. So, put all these values have been substituted, here, right, substituted. So, Si4 is equal to, then it is after simplification 0.87002 minus 2.976 into 10 to the minus 5 minus 0.05174, Si4 is coming 0.81825, that is the voltage stability index value at node 4. So, this is Si2 is 0.94378, Si3 0.86924, Si4 is 0.81825. That means, your minimum of all this is 0.81825, that is Si4, that means k is equal to 4. Here it is your k, Sik, k is equal to node 4. So, node 4 is the most sensitive to the voltage collapse. This is of course true, because it is a small radial network, main feeder type, there is no your what you call no lateral branches or other thing. Otherwise, suppose if you have a distribution network like this, say this one you have, right, you have a network like this, and suppose you have a lateral branches, right. Suppose you have a lateral branches like this, suppose you have a lateral branches, there is, it is your guarantee that this node, last node, or this last node, or this will, out of these 4, one will be more sensitive to a voltage collapse. No, there is no guarantee that, right. This is of course substation. So, you have to find out actually your what you call that each node SI value and increase the load at every node. You may find these are the this node, or this node, or this node, last node may not be your one of them may not be sensitive to voltage collapse, it may become some other node, depend on the load characteristic, Rx values, right, and your load values, how it is. So, it is not that your what we call the example we took, it is a very small example, it is only 4 nodes. So, this node is coming actually sensitive to the voltage collapse. In reality it you may have many laterals, but does not mean any of these lateral or main feeder end node will be sensitive to the voltage collapse. No, it depends on the load, Rx values of the your what you call Rx value of the your each branch load, and at the same time also substation voltage level, many factors are there. So, but for this example it is showing that this node is more sensitive to the voltage collapse, but which load it will be collapsing, that you have to increase the load, and you have to see when there will be no solution of the voltage magnitude for node 4, at that time it will be collapsing. So, this voltage stability index, that is the voltage stability of radial distribution network, and whether it is for a your what we call if you there are many other versions of there for voltage stability index, right, of radial distribution networks, but here only as per the classroom purpose we want to solve. That is why for this thing, suppose a load flow will be given, I will suggest one thing to you for this example, for that 4 bus example. For 4 bus example, what you can do is that just check what you can do, you neglect the losses. So, if you neglect the losses, we have computed V2, V3 and V4 in the second method by neglecting the losses. Suppose loss is neglected, you just yourself compute what is the value of SI2, SI3 and your SI4, right. Just neglect the losses. These results are available up in the very first iteration when branch losses are neglected, right. And with loss neglected, you just try to find out what are this what are the value of the stability index and which one will be more sensitive to voltage collapse. You will find again it is node 4, because it is a simple 4 bus problem. In the class we cannot go beyond that, right, as far as classroom exercise is concerned. With this distributional load flow and your voltage stability, your what you call index, now it is complete, right. Only thing is that in the assignment, another thing you have to do very seriously, and good problems will be given in the assignment, and just your job will be to your what you call to solve those things, right. And compared to the your power system analysis course, where also heavy computation was there, here also huge computation is there, but we will see that we will think of all these things. I have thought over that. The problem will be given in such a fashion such that you can do it quickly, right, without calculating too much, right. But these are the basic thing. Now, another thing is that approximate method for distribution system analysis. Approximate method means, suppose this diagram is there, or this is, forget about this thing, you for the time being you forget about this thing. Suppose this is R, this is sending end voltage, this is receiving end voltage, and this is VR, right, and load is lagging. So, current is lagging. Now, if you your what you call, if you draw the your long line, short line, medium line, long line, those phasor diagram, go to that short line phasor diagram. Then if you take this is reference, this is my VR and current is lagging. So, this is my current I, right, this angle is theta, therefore, this is your same thing parallel to this line, somehow it will be parallel to this line. So, this term is will be your IR, because I have taken small r small x resistance reactance IR, and this is 90 degree with this, right, and this is will be just somewhere here it is coming, right. So, this is your Ix, I is the magnitude of the current, right, and this is your Iz, right, and this is your Vs. This angle is delta, right, and this angle is theta. So, if you draw a horizontal line, and this one is again theta, right. So, this is your 90 degree, this is your 90 degree, this is your 90 degree minus theta, that means this angle is theta, that means this angle is 90 degree minus theta, right. And if you draw a vertical line and this thing, right, and then your let me write down here this equation. So, this point is A, this point is, suppose I am drawing a vertical line from here, this point is B and this point is C, that means this is your say B dash, this is your C dash, right. Therefore, what is AB? AB is equal to your, this portion is IR, so IR cos theta. Then what is BC? BC actually is equal to B dash C dash, right, is equal to your, this is IX cos 90 degree minus theta, right, IX cos 90 degree minus theta is equal to IX sin theta. Then your VS, then your AC, first you find out AC. AC is equal to AB plus your B dash C dash, B dash C dash and BC same, right. So, that is your IR, I have used small r, no, it should be small r. So, I small r cos theta plus I small x sin theta, right. Therefore, your Vs cos delta, you take the, this is your delta. So, take the projection on that. So, Vs cos delta actually, if it is your O, so Vs cos delta will be actually OC is equal to OA, that is your VR plus AB plus your BC, that means Vs cos delta will be is equal to OA is VR, this OA is VR, right, this OA is VR. Therefore, it should be VR plus I you take common these two term, it will be R cos theta plus x sin theta, right. But this angle delta actually is very small, right, delta actually is very small. So, delta actually very small, right, that means cos delta approximately 1.0, right. That means this approximate equation of Vs will be VR plus I, then R cos theta plus x sin theta, right. That means this is actually, that means Vs minus Vr is equal to I R cos theta plus x sin theta. So, this is actually voltage drop, right. This is the approximate way of calculation, right, because we have taken delta is very small. So, cos delta is 1. So, it will be Vs is equal to Vr plus I R cos theta plus I x sin theta, right. So, that is why in approximate method, right, in approximate method we will use this voltage drop, that means voltage drop, that means this one is actually I R cos theta plus x sin theta, right. So, starting with a numerical type of thing problem, assume that example, assume that the circuit shown in figure 1, this figure represent a balanced 3-phase circuit, power factor of the load is cos theta, right, that is that current power factor of this load current angle also, this is theta, right. So, power factor is cos theta, current is lagging with respect to VR, right. So, find the load power factor for which the voltage drop is maximum, right. So, the line voltage drop V d is equal to, just now we have seen voltage drop will be I R cos theta plus x sin theta, this is approximate one. So, I R cos theta plus x sin theta, right, just now we have seen. So, that means if you take the derivative with respect to theta, so d voltage drop d theta is equal to minus I R sin theta plus I x cos theta is equal to 0. Therefore, x by r will become tan theta, right, this is the relationship. Therefore, the theta max, that is will be tan inverse x by r, right. So, here it is tan theta. So, theta max, from here you will get theta is equal to tan inverse x by r, that is actually theta max, right. So, power factor is equal to cos theta max, that is cos tan inverse x by r. This means that if you if the your what you call, if that your power factor of the load, if it is like same as the your that impedance angle, then voltage drop will be maximum, right. So, next one is say example 2. So, this is a simple one I took. The next one is the example 2. Suppose in example 2 that figure 2, this is actually figure 2, right, this is figure 2. You have a distribution transformer here, and here there are 3 tapping points, that is 3 nodes are there, node A, node B and node C, the 3 nodes are there, right. So, in that case that branch impedance are given for actually here not marked anywhere. So, this is also marking one node by a point only, by a dot, right. So, this is 0.05 plus j 0.01 ohm, this is 0.1 plus j 0.02 ohm, right, and this one 0.05 plus j 0.05 ohm, and here in this case everything is given, that here no question of iteration or anything, because data results are given. Here it is drawing 30 ampere at unity power factor, this is given. Here it is drawing 20 ampere, but power factor is 0.5, right, lagging, and here 50 ampere, power factor is 0.9 lagging, right. So, first use the approximate voltage drop equation, that is voltage drop approximately is equal to I r cos theta plus x sin theta. This is the voltage drop equation just now we have seen, So, first I will so you have to find out voltage drop, the real power per phase of each load, and then C reactive power per phase of each load, and number D kV output and load power factor of the distribution transformer. This is actually distribution transformer. Here I am by bar I did not show the node, but later I will show you, right. So, first thing is how to calculate approximate method, right. So, this is the formula. So, what you do, the current is given at point A 30 ampere unity power factor, right. So, the voltage drop for each load can be calculated as 30 ampere is the current, right, I is there, then in bracket it is r cos theta plus x sin theta. So, r for this branch is 0.05 ohm, right. So, and cos theta is unity, so cos theta is 1. So, r into 1 plus your x 0.01 for this branch, x is 0.01 into that is unity power factor. So, sin theta is 0. So, sin theta is 0. So, that is 1.5 volt, but thing is that directly I am making it, but how I am getting it I will come later, right. Now, the voltage drop due to your what you call load at B, that is load at B. So, power factor here it is 0.5 lagging, power factor is 0.5 lagging, and for this branch 0.1 and j 0.02 ohm, right, this r is this one. So, for this was a VDR cos theta. So, at that time please take from this point to this point what is resistance and what is reactance, right. So, that is 0.05 plus 0.1, 0.05 plus 0.1 cos theta is 0.5, right, it is given, right. Similarly, from here it is 0.02 plus 0.01, 0.002 plus 0.01 or 0.01 plus 0.02 into it is cos theta. So, sin theta is equal to 0.866, that is due to load B multiplied by of course 30, because here also your this thing, this is actually 20, this is actually 20, because here it is 20 ampere, right, it is 20. So, this is actually 20 into that your I into r cos theta plus x sin theta. So, 2.02 volt. Similarly, due to this one 50 ampere it is there, power factor is 0.9 lagging, right. So, in this case you forget about this, you add R1, R2 and R3, right, 0.05 plus 0.1 plus 0.05 into cos theta. So, R1 plus R2 plus R3 into 0.9, right, 50 is there, I in there. Then similarly, x1 plus x2 plus x3, from here you calculate all the reactance 0.01 plus 0.02 plus 0.05. So, into your what you call cos theta is 0.9. So, sin theta will become 0.436, right. I am not calculating here, but power factor cos theta is given. So, sin theta 0.436. So, that is 10.744 volt. If you now add all these things, therefore, total voltage drop VDA plus VDB plus VDC, it becomes 1.5 plus 2.02 plus 10.744, that is 14.264 volt, right. So, but voltage of this figure 240 volt secondary your touch system, that means this point, suppose this point that is blue color, this point voltage is 240 volt, right. That means, if you compute in per unit, it will be 14.264 upon 240, that is 0.0594 per unit, right. So, this is the voltage drop. Now, question is how we are computing this approximate one. So, if you recall the load flow things, so what I will do, I will draw this one, this circuit again, and I will show you, but this one I showed directly such that quickly you can compute. After that exact calculation also will show. So, in this case, suppose you have, this is a distribution transformer, this is your node. So, this is suppose instead of 1, as suppose this is your node A, node B and node C. This is actually your node A, node B and node C. Here also node A, node, same thing I am drawing, but putting bar just to show this node, right. These are the node. So, everywhere current is known, everywhere current is known, these currents are known. So, this current is I A, then this load current is I B, this is I C. So, I A, I B, I C at load point A, tapping point A, B, C, these are known, right, with their power, your power factor also known, right. So, they one is unity, another is lagging power factor, other two are lagging power factor, right. And this is your substation, this node, this is substation, and this is your distribution transformer. Say this node is O, right. So, then what is the current? What is this current flowing through this branch? Suppose this is your I 1, this is your I 2 and this is your I 3. There are 3 branches, right. That means, I 1 is equal to your I A plus I B plus I C, right. Here similarly, I 2 is equal to I B plus I C and I 3 is equal to your I C, the same current is going to the load, I 3 is equal to I C. So, I 1, I 2 everything you know. Then when you calculate the your this voltage is say V O, this voltage say V A, this voltage say V B, this voltage is V C, right. Therefore, and impedance of this branch also given, all this branch given, say impedance is Z 1, it is Z 2, it is Z 3, this is given. Therefore, if you when you write the equation V A is equal to V O, that means this voltage V O minus I 1 Z 1, right. So, if you think like that, therefore, what is your what you call that I 1 Z 1, that voltage drop, right. So, I 1 is equal to I A plus I B plus I C, right. So, if you write V A is equal to your V 0 minus I 1 is I A plus I B plus I C into Z 1, Z 1 means R 1 plus J X 1, this branch 1, right. This is your first voltage drop I A plus I B plus I C R 1 plus J X 1, right. Similarly, that is your what you call in terms of I A plus I B plus I C. Similarly, if you write V B is equal to V A minus I 2 Z 2, right. So, that will become actually this one become I 2 is I B plus I C into R 2 plus J X 2, right. So, this is your V B. Similarly, your V C will be from this graph, from this figure only, V C will be V B minus I 3 into Z 3 is equal to V B minus I 3 into Z 3, that is I 3 is nothing but I C into your Z 3 is equal to R 3 plus J X 3, right. So, what we are doing is the total voltage drop and this that. So, this is here for the branch 1 voltage drop, this is your branch 2 your this actually it is actually V A minus this one. So, this is branch 2 voltage drop and this is your branch 3 voltage drop, right. If you add all this voltage drop, just for the sake of understanding. So, this is your if you add all I A plus I B plus I C into R 1 plus J X 1 plus then other voltage drop is I B plus I C into R 2 plus J X 2 and last one is I C into R 3 plus J X 3, right. This way if you make, then you will see that first is I A, this I A into R 1. So, it is your I A into R 1, right, this term. Now, when you take I B into R 1, I B into R 2, that means your I B your R 1 plus R 2, right. Now, when you take I C into R 1, then your I C into R 2 and I C into R 3. So, I C R 1 plus R 2 plus R 3, this is the real part. But similarly, the reactive part it will be J, right, it will be J, then it will be I A x 1 plus I B x 1 plus x 2 plus I C x 1 plus x 2 plus x 3. Thank you. We will be back.